In this video, we're going to discuss phase changes and understand a heat graph, and we'll introduce latent heat. There's a little formula for it as well. So, phase changes. So basically, it's when a solid can turn into a liquid, which will turn into a gas. Of course, if a solid melts, it becomes a liquid, and if it boils or evaporates, it will become a gas. That gas can condense to become a liquid, and then freeze to become a solid. So, for example, water would have three states: solid, liquid, or a gas. Question now is, if you add heat, will it always lead to a rise in temperature? Actually, you'll find no. It can lead to a phase change. That is when the energy that you're adding now doesn't increase the temperature anymore. It starts melting or vaporizing. This is happening at a constant temperature. The temperature will not change during this period. Okay, that's when you'll get freezing or vaporization or melting and gas-liquid condensation, the things that we just discussed. You can go directly from a solid to a gas doing sublimation, by the way, but that's not important right now. So here is an example graph that we need to know. If we take ice, or just 1 gram of water, which is at minus 30 degrees, that is ice. It's going to add energy, you're adding energy. So it gets hotter, hotter, the temperature is increasing until you reach here. Something is happening here. This is when the ice becomes water. Okay, so this is where you'd have not vaporization, this is where you would have fusion. So this becomes water. Once it becomes water, you keep adding more energy. It'll keep going up. Water will get hotter, hotter, hotter until water reaches its boiling point. That's 100 degrees. So now it takes a little bit longer, it takes more energy. You can see a lot of energy. Water needs a lot of energy to turn into steam, and eventually it will turn into steam, and then it'll increase its temperature again. So at points B and D, this is when they're undergoing a phase change. A, C, and E is simply increasing the temperature. Okay, so you could calculate the Cm delta T, you can calculate the latent heat, which is what we're actually going to do next. So I've just mentioned where fusion and vaporization is. There is fusion and there is vaporization. Amazing. The formula that we would use is energy, or Q, remember sometimes it's written as E, it's interchangeable. Energy equals M, the mass, multiplied by L, the latent heat. Every material has its own requirements of energy to make the phase change happen. So if you're adding heat, it would be positive. If you're losing heat, it would be negative. Okay? So you can see that different substances have different melting points, which means they have different latent heats, different boiling points, and different latent heats. You'll be given the information that you need, so you don't need to memorize anything in any tables. They'll be given to you. So here's an example. How much heat energy will be needed to totally melt a 1.5 kilogram block of ice at 0 degrees to get to water? So the information that we have is this: the latent heat has been given, it's from the table. So if I just want to find it, EH or Q, it doesn't matter what I want to call it, equals ml. I will simply multiply them, 1.5, and I'm going to multiply that by 3.34 times 10. Forgive my handwriting, I'm using a new mouse and it's not very good. So 1.5 multiplied by 3.34 times 10 to the power of 5, and you would get a big number: 501,123 joules. Energy is in joules. Very nice. We're melting, temperature is going up. We'll keep it as positive. Okay, another example will be the same thing. How much extra heat is needed to convert water into steam? So you have now got to find the new energy. So you have a different latent heat of vaporization. You can see that it is a bigger number. You plug the numbers in and you will get a nice huge number. Okay, there were two types that I mentioned. Latent heat of vaporization is when a liquid turns into a gas, or a gas turns into a liquid. No change in temperature. Latent heat of fusion is the same idea, but when it's a solid turning into liquid, or a liquid turning into a solid. So this is an example of fusion. You will have this all happening at the same temperature. The solid and the liquid, they will be swapping. So either the liquid turns into a solid or the solid turns into a liquid. Vaporization, similar idea like I mentioned, the liquid will turn into a vapor or a gas, or vice versa. So here's a quick summary table of what I have just discussed. You will see that the solid to liquid will be a fusion, energy is absorbed. Liquid to a gas is vaporization, energy is absorbed. Gas to a liquid, I'm losing energy, so energy is emitted, it's given away, energy is lost, it's going out. Liquid to solid, same thing, fusion, energy is emitted. Here is a big problem that we would have to perhaps solve. Calculate the amount of heat required to convert 50 grams of ice to steam. The specific heat capacity of water is this, the specific latent heat of fusion is this, and the heat of vaporization is this. So you'll see that there are multiple stages. You're going to have to take your ice, you're going to have to melt it to water, that will be stage 1. Then you take the water and you raise the temperature to 100 degrees, that will be stage 2. And then it turns into steam, that's stage 3. 3 steps to solve this problem. So we have step 1, the melting of the ice, step 2, the heating of the water, step 3, final step, vaporization. So let's do it one at a time. Step 1, we're going to convert the solid into a liquid, so latent heat of fusion, Q equals ml or E equals ml. The mass which we had was 0.050, times by 334, which was given in the previous slide. That's 16.7 kilojoules, 16,700. Okay, stage 1 is done. Let's look at stage 2. We're going to take this water that we've just melted and we're going to turn it into 100 degrees. That's when we use the formula from the previous lesson. E equals Cm delta T. Delta was a little triangle. Cm delta T. The mass is the same, multiplied by 4.18. This is the specific heat capacity of water. Multiplied by the change in temperature from 100 minus 0. Final minus initial is just 100. And you multiply that together and you'll get 20.9 kilojoules. That's stage 2 done. So we'll add that to stage 1, but we'll do that at the end. Stage 3 is now when you are going to vaporize it. From the 100 degrees Celsius of the water, we'll turn it into steam. Again, this is going to be Q equals ml. That's the latent heat of vaporization now. So M times L. 0.05 times the vaporization number, which was 2260, 113 kilojoules. So you'll simply add all 3 numbers. Remember, 16.7 plus 20.9 plus 113. The total energy needed is roughly 151 kilojoules of energy.